Okay, good.
All right, everybody. This week, Javier Siemens visiting us from University of Wisconsin-Milwaukee. So Javier did his grad school at Tufts with Andre Blanken, and then
Alex.
Alex. And then he and I overlapped in Milwaukee for a little bit while he did his postdoc, and then from there he moved on to Caltech, and then now back to Milwaukee where he's a faculty position. He's seen his own Phil Chang. So.
All right, thank you. Thanks. It's a pleasure to be here. It's actually my first time. I was kind of surprised. I've never been here, never visited before. So I'm going to tell you about detection of low-frequency gravitational waves with pulsars, and I'm going to start with a few slides, probably about maybe about a quarter of the talk is sort of really a big picture type of talk, and then I wanted to go into a few of the details. And so in particular, there's a really nice, easy, I think, calculation that to show what the effect of a gravitational wave is on the pulsar Earth baseline. I will talk a little bit about how one analyzes pulsar timing data. And then I will also talk about some simulations that we've been doing recently regarding the time to detection and some interesting things that we found out about sort of surprising ways in which the signal-to-noise ratio scales. And then I will talk about testing gravity with gravitational waves. This is kind of a lot of stuff. I don't actually know exactly. So later on, as the time progresses, some of this stuff may not be as thoroughly discussed, and especially because I encourage you to ask questions and interrupt. I prefer a much more informal type of talk. So if you want to spend more time talking about something rather than something else, that's fine by me. Okay, so about 5 years ago, I joined a collaboration called NanoGrav, which is the North American Nanohertz Observatory for Gravitational Waves. And it consists of about 50 students in the US and Canada. So here in Canada, we have people at UBC. The lead of the group there is Ingrid Stairs. And at McGill, it's Vicky Caspi, so she has the group there as well. And then a bunch of people in the US. And this is really part of a worldwide effort that includes similar groups in Europe, the European Pulsar Timing Array, and Australia, the Parkes Pulsar Timing Array. And the way these three collaborations work is that we have a consortium of consortia called the International Pulsar Timing Array. And what we do is we sort of, we each have our own set of telescopes, our own data, and we analyze it in a sort of a competitive way, but then we share, we put all our data together, and by putting all our data together, we can do better than obviously than just each of our own data independently. Different groups are looking at different pulsars, and they also, but even where there's overlap, of course, if we just merge the two data sets together, you have a higher cadence data set, which is a good thing. So gravitational waves, so ripples in space-time, they propagate at the speed of light and are a key prediction of general relativity, which have thus far eluded direct detection. And I'll say a little bit about what I mean by direct. They're produced by massive objects when they move rapidly, and they change the distance between freely falling objects. So here's a cartoon of a gravitational wave going into the board and its effect on a ring of masses. There's actually, just like in electromagnetism, gravity, general relativity has two polarizations. And this one was called the plus polarization, and there's the same picture but rotated 45 degrees called the cross polarization. It's a very similar situation to electromagnetism, where we also have two polarizations. If you put a test charge, one of the polarizations will move it up and down, and the other one will move it from side to side. And a general electromagnetic wave is a linear superposition of those two motions, basically a wave that would result in those two motions. Similarly with gravitational waves, but gravity is a tensor force, or is the force that's best described by a tensor rather than a vector, and so it's easiest to see its effect by studying a ring of particles, because it's actually acting in two directions at once, not like electromagnetism, in which each polarization only acts in one direction. The strength of the waves is measured by a quantity called the strain, which is just the fractional displacement of, say, this top mass. And the typical strains that we measure in the kinds of experiments in pulsar timing experiments is 10 to the minus 15. And I'll give a very short derivation of where this number comes from. And of course, our goal is to provide a new means to study the universe. We already have evidence for gravitational waves. Halston Taylor got a Nobel Prize for it in 1993. And what they found, as I'm sure you all know, is orbital decay, which is consistent with gravitational wave emission. And I have this slide up. I like to show this slide because every once in a while, less so more recently, but every once in a while someone's asked me what the big deal is. What are we trying to do? Haven't we already seen gravitational waves? And the point is not to find evidence of gravitational waves, not to detect them. That's the first step, is detecting them. The point is to build an observatory, to build a telescope, to see what the universe looks like using gravitational waves, just like we have electromagnetic telescopes. And of course, you can't do that with a Halls-Taylor binary. Now, pulsar timing arrays are part of an array of experiments, which I show here. So on the y-axis, I have the strain, so this fractional displacement versus frequency in hertz. These are put in sort of approximate places here. At the highest frequencies, we have ground-based instruments such as LIGO that Kip works on. At sort of 10 to the minus 4 hertz or so, we have space-based instruments, which unfortunately don't look like they're going to happen in a really long time. I think the launch date now for ELISA is 2034, which is kind of sad. And then at the very lowest frequencies, we have cosmic microwave background experiments. I'm sure we've all heard about that earlier this year. And each of these, because they are sensitive to different frequencies, they are probing different source classes and different types of sources. So here, at the very highest frequencies, we have neutron star mergers and black hole mergers. Yes, so stellar mass type objects, or maybe tens of stellar masses type compact objects. And at pulsar timing array frequencies at 10 to the minus 8 hertz or so, those experiments are sensitive to the gravitational waves produced by supermassive black hole binaries, and also primordial gravitational waves, things like phase transitions and inflation. And all these three experiments actually work in exactly the same way. All it is just measuring the change in the light travel time that a gravitational wave produces between two objects. In our case, for pulsar timing arrays, it's just the distance between the pulsar and the Earth. For LIGO, it's just the distance between one of the mirrors, at the end of the vacuum tubes and the beam splitter. So it's this is the hope here, and I think it's important to make an analogy with electromagnetic observations. The hope here is actually to open up a new window, have a new way of looking at the universe. And just like different windows in the electromagnetic spectrum paint complementary pictures of the universe, different gravitational wave, we expect different gravitational wave frequencies to also paint different pictures. Again, because of the different source classes. Okay, so I mentioned already supermassive binary black holes. These are the most promising sources of gravitational waves at the frequencies that pulsar timing experiments are sensitive to. The idea is, it comes from the hierarchical, the ideas that people have for the formation of galaxies. So the size and composition of galaxies as we see them today is thought to arise from a hierarchical process where you have smaller galaxies early on in the universe that merge to form slightly bigger ones, and then those slightly bigger ones merge, and so on, until you get to the size and composition of the galaxies that we see today. Galaxies host supermassive black holes at their centers, and when the galaxies merge, eventually the black holes will find each other, orbit, decay gravitationally, emitting gravitational waves. And the types of signals that they produce, starting from the bottom here in this cartoon, this is something called a burst with memory. This is I'll have a little bit more to say about that later. Produced in the final merger of the black hole of the black hole binary. When they're further apart, they produce this green type of wave. So this is basically a periodic wave. So that's when they're far apart, and then all the superposition of all the bursts and all the continuous waves from all the black holes that ever merged in the history of the universe produces this red curve, which is a stochastic background, a signal that we cannot, that is not resolvable into individual sources. So the analog of the cosmic microwave background in light, in gravity. And now there are other sources as well, which I won't discuss except here, which include somewhat more exotic sources like cosmic strings, inflation, and also phase transitions.
But what is the relative amplitude of all those different signals? So you say, I know it's kind enough distance for a supermassive black hole binary.
So they're all sort of around the 10 to the minus 15-ish number that I quoted before. And also, the stochastic background is kind of a tricky one because it's really a spectrum. It's best described by a spectrum. So it's sort of the overall amplitude of that spectrum at a particular frequency. So you pick your frequency, and then you can sort of set an amplitude that way. These individual ones, it depends on the chirp mass of the binary. It depends on how far away they are. But again, 10 to the minus 15, 10 to the minus 16, sometimes perhaps bigger if they happen to be closer. And these are the smallest ones of all. These are more like 10 to the minus 16 or something like that. So typically, the burst of memory effect is about an order of magnitude smaller than the sort of main waveform. OK, so how do we do this experiment? So we use these objects called pulsars, which are a type of neutron star. They have strong magnetic fields. They spin rapidly, and they emit beams of radio waves along their magnetic axes by a mechanism which I understand is still under the details still have to be worked out. It turns out that doesn't matter for our experiment. So here's a picture of a pulsar. Right in the middle here, we have a rotation axis, and then a magnetic axis. And then as the pulsar is rotating around, if the line of sight between the Earth and the pulsar and that beam of radio waves meet at any point in the rotation, then you observe these pulsars as sources of radio bursts. And they rotate with periods of milliseconds to seconds, and you can think of it basically like a lighthouse. And millisecond pulsars, in particular, have periods of 20 milliseconds, and they rotate rapidly with a stability that rivals the stability of atomic clocks. And these millisecond pulsars, the ones that are particularly useful, are so-called recycled pulsars. They're pulsars that have been in a binary. They have accreted material from a companion. In the process, they have sped up, so become very, very fast rotators, and also become kind of boring. So the magnetic fields are not as large, and they're more stable. So they're very, very stable. And so, for example, a couple of weeks ago, the period of one of our pulsars, our best pulsar, was this. There are 15 zeros here between the decimal point and the 1. And we not only know how fast it's rotating right now, or now-ish, but also we can predict 5 years from now how fast it will be rotating to extreme accuracy with these models. So, right, and these pulsars do not glitch, or that's the hope. We haven't observed them to glitch. So we can exploit this stability to measure gravitational waves. So here's sort of a cartoon of the gravitational wave. Here's the pulsar. Here's the Earth with a gigantic radio telescope on it. And as the gravitational wave is going through, it is changing the distance between the Earth and the pulsar, or if you like a different description, it is redshifting and blueshifting the signal from the pulsar in a way which I will compute shortly. Now it's not enough to have just one pulsar. You need lots of pulsars. We want to build a galactic scale gravitational wave detector. And the reason we need lots of pulsars is because it's not good enough that you see a signal in one of the pulsars, because you don't know. It could be, for example, what you said. It could be a glitch. Actually, a burst with memory. If you see it in a signal, a glitch is just a change in the frequency, right? A burst of memory has exactly that effect. It just changes the frequency. If we only see that in one pulsar, we can't say that isn't a glitch. But if we see changes in the frequency that occur simultaneously in all of our pulsars and in a particular correlated way, then we can say that is much more likely to be a gravitational wave. If we have a bunch of pulsars, then we can look for these correlations. And in the case of the stochastic background, you get this picture down here, which is called the Hellings and Downs curve. And this is the correlation in the deviation from the expected arrival time of a pulse, of pulses from two pulsars, separated by an angular separation given on the x-axis. So I have two pulsars, one is over here, another one's over here. They have a certain angular separation. As I vary that, the degree to which the deviations from the expected arrival times of pulses is correlated is given by this curve. So over here, they're very correlated. Down here, near 90 degrees, they're anti-correlated. And as I go to, OK, good. And as I go to 180 degrees, it becomes more correlated again. So we use the two best radio telescopes in the world. Arecibo is the largest radio telescope in the world. And Green Bank is the world's largest steerable radio telescope. And that basically buys us the best data for this type of experiment. Some of you in this room probably know this. That's CHIME, which stands for Canadian H1 Mapping Experiment. Good. That will contribute to our data sets at low frequency. So this is an instrument, my understanding. So Vicky Caspi actually is the one who's most heavily involved in this. Is that this experiment will actually provide us with data around 400 megahertz or so. And that will actually be quite helpful because it means we can, we need to do, in order to correct for interstellar propagation effects, there's a dispersion basically that occurs because of the interstellar medium. We need to correct for that, so we need to do measurements at different frequencies to not only measure what the interstellar medium is doing between the Earth and the pulsar now, but also to track it in time, how it changes in time. And so we actually do measurements at two frequencies at both of these, using both of these telescopes. And of course, if we can have a telescope that basically gives us times of arrival of pulses at 400 megahertz, then we can free up telescope time. And this is particularly useful for the GBT because of what latitudes are observable by CHIME and the GBT. So this is what our data sets look like. And I will tell you, this is a little bit out of order. I'm going to tell you later how we produce these, but I just wanted to show you this now. So this is time in years here. These are the residuals in so the axis here is microseconds. The red shows some data that was taken with an old back end, and this data now with a much wider band back end. We've gone from I think 64 megahertz to about 800 megahertz basically in terms of bandwidth, and that means that our data has become much more precise for most of our pulsars. So factor of 5 here, and a factor of 5 again, also, or so there. So, and this is what our data looks like. We observe right now it's about 42. I think this number is a little bit out of date. Actually, I think it's closer to 50 now at the GBT and Arecibo about every 3 weeks. And this is the data set that we search for gravitational waves. And it looks if it looks a little scary, it should. So what kinds of things do we do? The main goal is to detect and characterize low-frequency gravitational waves. We are working on developing a set of codes and making them publicly available, so everything is going to be on GitHub, et cetera. And this is kind of in reverse order to which it happens. That we have a bunch of people dedicated to generating the data and curating the data. So we try to have regular data releases. We're about to have one now. Our goal is to have one every 18 months. We're developing new pulsar timing packages. This is important. Turns out there's really only one independent pulsar timing package. So the package that actually takes your times of arrival and turns them into these residuals. It's called Tempo. That was developed in the 70s, in the late 70s, I think. And has bits of Fortran in it. It's pretty old school. And but that's not really the problem. The problem is that there's just one package. And I think the moment that we claim a detection, people are going to say, well, okay, they're going to want to see some robustness in terms of that result. So that's important. And then there's a bunch of people that are doing detector construction, which is a sort of a nice way of saying we're searching for new millisecond pulsars to add to the pulsar timing array, and developing more efficient and sensitive pulsar searches and radio data, and then equally important, or perhaps one of the most important things that we do is this detector characterization. So each pulsar is it's like a snowflake. So it's different and special in its own way. And we really need to understand its properties, the interstellar medium, how the interstellar medium in that particular line of sight evolves, and so on. So, so here's a plot that shows the strain and this is a stochastic background plot as a function of time in years. And there's a few curves here, which I will explain in a second. So this is the expected amplitude of the supermassive black hole, supermassive binary black hole background, the range that we expect it to be in. And this is actually, to be specific, since somebody asked earlier, this is the amplitude at 1 year, at the frequency of 1 over 1 year. Okay. Because it's basically it's a red noise process, stochastic red noise process. And this is the range that we expect. The red curve is the upper limit that we would set in the absence of a signal as a function of time. The green curve is the amplitude that we detect with 50% probability, or 50% of realizations of the universe. And the blue curve is the amplitude that we would detect in 90% of universes. And this is the upper limit we set. It was published sort of very recently, so last year, or about a year and a half ago now. And this was data that we took from between 2005 and 2010. This is the projected sensitivity with data going up to 2014. And this is where we actually find ourselves, so a little bit higher. The estimates that we did here were very simplistic. We actually took our 5-year data set and said, OK, we're discovering pulsars at this rate. This is the quality of pulsars that we have. And it was pretty crude. I think it's pretty amazing that the agreement is so close, given that we sort of projected into the future by a long way, adding pulsars that we didn't in a more or less in a consistent but somewhat arbitrary way. And we still came pretty close. The important thing is that this preliminary upper limit is already in this gray area. So this is already in astrophysically interesting territory, in a place where we expect a signal might be. And also there's in the next few years, we actually have a chance of, say by 2022, having discovered with 90% probability the sort of 1 sigma lower bound on the amplitude of this background. So this is quite promising, I think, for years to come. And so it's not obviously not just about making that detection, but trying to paint a picture of the low frequency gravitational wave sky. So that will be the and so just to summarize here, we want to detect and study individual supermassive black holes along with their collective signal, and that will tell us things about the physics of accretion and galaxy formation, the hierarchical model of galaxy formation. I've also mentioned sort of more exotic things like cosmic strings and things to do with high energy physics. Mentioned the black hole merger memory effect. This is a nonlinear effect in gravity. And of course, there's always the surprises. We don't know we know we have some ideas about what's there, but often we're surprised.
What mass ranges of the massive black holes would you be most concerned?
It's 10 to the 8, 10 to the 9. The higher, the better. Basically, I think 10 to the 8 is the very minimum. 10 to the 9 is yeah. Okay, so let's see. I have. So how long does the seminar last? Till the hour. So I have 25 minutes. Okay. That took quite a long time. Okay. So very quickly, I want to tell you about the effect of a gravitational wave on the Earth pulsar system. So here's the pulsar. Here's the Earth. There's a gravitational wave going in the direction omega hat, and the vector p hat is a unit vector that points in the direction of the pulsar. We have a metric perturbation given by this formula. This is just an arbitrary wave, a wave that is arbitrary other than the fact that it's traveling in direction omega hat. So it doesn't have to be like a plane wave. It doesn't have to be a sinusoid. It can be anything, but it can only be traveling in that one direction. This is S super A is the vector tangent to the trajectory of the photon that propagates from the pulsar to the Earth, and therefore has this time component, which is the frequency, and then minus p hat, because it's going in the opposite direction of p hat. We can perturb the tangent to the null geodesics by introducing these gravitational waves, and that will just be given to the unperturbed tangent vector times some small perturbation. And then we can write a geodesic equation for the zeroth component of this vector here, because that's the frequency. That's actually what we want. It's very easy to write. That's just given by this expression here. It's just minus a half times the time derivative of the metric perturbation projected onto these two tangent vectors. And we expand these in terms of their unperturbed plus a perturbation, and we keep the first order terms. Then we arrive at an expression like this. So that's the zeroth component of this tangent vector, the derivative of that with respect to the affine parameter lambda. It's just the time derivative of the metric perturbation times the frequency squared projected onto the line of sight that connects the pulsar and the Earth. So that's the equation that I just wrote down. Here we have a derivative with respect to affine parameter. Here we have a derivative with respect to time. So we got to connect the two. And we have a connection because we know what, along the photon trajectory, dt by d lambda is just nu, and dx by d lambda is just p hat times nu, right? Just what we've had in the previous equation. And so we can connect these two derivatives, and now we can put the derivatives, two derivatives of the same thing on either side, and integrate. And of course, it's the total derivative. So all it depends on is what's going on at the endpoints. In particular, you can solve for the redshift, which is the difference in the Earth, what we see minus what was emitted divided by what was emitted at the pulsar. This is one of the quantities that we talk about. Is just the difference in the metric perturbation on Earth when the pulse is received minus the metric perturbation at the pulsar when the pulse was emitted. So this is just the bounds on the integral are lambda emitted and lambda received. That's these two metric perturbations here. Projected onto the line of sight that connects the Earth and the pulsar, and then there's this sort of funny geometric factor here in the denominator that is associated with the relationship between affine parameter, the derivative with respect to the affine parameter, and the derivative with respect to time. So, okay, so let me now tell you a little bit more about this data. Okay, good. Tell you a little bit more about this data. So I mentioned earlier that we look for gravitational waves in residuals. So where do these residuals actually come from? So we keep track of every rotation the pulsar does over the course of many years. And we can actually predict with high accuracy when a particular pulse is going to arrive. Remember, I showed you this amazing accuracy that we can predict the frequency to in one of our pulsars. And we construct a model for when each pulse is supposed to arrive. And then, this is the model we have here. We construct it this year. We wait a year. And a year later, we have a time of arrival that we predict. And the actual time of arrival of a particular pulse happens to be a little bit later. And the residual is the difference between the actual arrival and the predicted arrival. Now, gravitational waves change the time of arrival of pulses. So we actually look for gravitational waves in this data set. So these measurements we do a few times. Actually, it's more like, well, maybe a couple of times a month for a few years. And this is a plot of some other plot of residuals that are not particularly accurate. But just looking at this plot, you can see that the lowest gravitational wave frequency that we're sensitive to will be set by the observational length. So you can maybe catch, a big, half a sinusoid or something like that of a period 1/7 years. The highest frequency is set by the Nyquist frequency, how often we sample. Of course, it's not. There is no Nyquist frequency because this data set is irregularly sampled. But clearly, if I'm not sampling any more regularly than once a month, I'm not going to be sensitive to gravitational waves with periods of less than a month. But this is very different data from probably the data sets that at least me coming from LIGO into this, I was not used to this. The data is regularly sampled. There's the points all have different error bars. And it turns out, and the upshot of this is that really we can't use frequency domain methods to analyze this data. We really have to basically use time domain techniques, which slow the calculations down. So this is a plot of the sensitivity, and so I'm going to try to tie the last 3 slides together into this plot. So here we have something called the characteristic strain, which is a dimensionless measure of the strain sensitivity as a function of frequency. So I said that we keep track of rotations, and then we basically create a model for when a pulse is going to arrive. And what we're basically doing is keeping track of the orbital phase of the pulsar. So here's the orbital phase, and there's some fixed initial constant that we don't know. And then, of course, the phase changes linearly with the frequency. The pulsar is also spinning down because it is emitting electromagnetic radiation. So that introduces a quadratic term into the evolution of the phase. Then it might be in a binary. And then we have to, the pulse arrival times actually change as the pulsar is going around its companion. We have to model that. Depending on where it is in the sky, as the Earth moves around the sun, the time of arrival will change. And all of these things are basically enough to explain the sort of V shape that you see in this curve. First of all, At low frequencies, you lose sensitivity. You have less sensitivity at low frequencies. Why is that? Well, the reason is that we're subtracting a frequency. We're basically subtracting out a quadratic. And if you have a low frequency sinusoid in your data, that looks a lot like a quadratic. Right? And you're actually taking that out. So as you go to low frequencies, or a linear piece, suppose you have a, some linear trend, you basically subtract all that out. That's very low frequency stuff that you're taking out in this way.
Actually, periods like 100 years.
These guys?
No, that's like 10 to the minus 9. Right?
Yeah, this is like 30 years, right? Yeah. Let's see, 3 times 10 to the minus 8 is 1 year. So 3 times 10 to the minus 9 is 10 years. Yeah, so 10 to the minus 9 is 30 years, yeah.
Isn't the peak just the Earth orbit?
Yeah, this one here? Yeah, that's exactly right. Yeah, I was just getting to that. That's exactly right. So this peak over here is at a frequency of 1 over a year, and of course, we're subtracting stuff out that has a yearly modulation to it. We're not sensitive to gravitational waves whose period is a year. This little guy over here is actually parallax, because we also, in some of these pulsars, we actually also fit for parallax. So that explains this guy here and this guy, and then these features that we see in our data. Up here, what's going on is that the timing residuals are white, and the timing residuals are the integral of the strain. And so when you turn those into strain, then you basically bring up a factor of the frequency here. It's actually a secret. It's actually a secret f to the 1/2 in here as well, but it doesn't matter. The point is, timing residuals are white, and when you turn that into strain, you lose sensitivity at high frequencies. So this curve, I'm sure you've had LIGO talks here before. It's a very similar shape to LIGO, but the sources of things at various different frequencies are completely different. Okay, so where does this 10 to the minus 15 number that I keep throwing around come from in the strain? So the pulsar timing experiments, as I've mentioned, they measure the residuals, not the redshifts. So that's the differences in the time of arrival. Those are just the integral of the redshift. So if you write this in the frequency domain, that's just basically like h over f. The RMS of typical pulsars that we have is about 100 nanoseconds. If you set the frequency to about 10 to the minus 8 hertz, then that gives you a strain. So a strain of this amplitude or higher would start to show a signal, would start to become visible in a time series with timing residuals of about 100 nanoseconds if the period or if the frequency is 10 to the minus 8 hertz. Okay, so this is going a lot more slowly than I thought. So I think I'm going to skip. This stuff and hope that I don't need it later. Okay. Okay. So I wanted to tell you now a little bit about the simulations that we've been running. So those are the plot that I showed you with the red, the blue, and the green curves that tell you when we're going to detect things or what upper limit we've set. So for many years, many of us, myself included, we've kind of used like a theorist's pulsar timing array. So we said, oh, what happens if we have an array with 20 pulsars at 100 nanoseconds, root mean RMS noise, and we time it for 5 to 10 years? What will our sensitivity be? We have an actual pulsar timing array, so we actually wanted to simulate this array with some realistic properties that we can measure in the data that we have. So one of the things was that the understanding of this is maybe a year and a half ago that this happened. The understanding was that the signal-to-noise ratio in the cross-correlation grows like some large power of time. And so all we have to do is just wait. And if you've seen pulsar timing talks, people have said, I myself even have said this, that all we have to do is just sit there, we just wait. And then we ran our simulations with our realistic pulsar timing array. And we were surprised, and not in a particularly good way. So then we went back and started simulating the sort of theorist pulsar timing array. And we saw that this idea that the signal to noise ratio in the cross correlation grows as a large power of time is actually not right. So we went back and started studying the scaling properties of the optimal cross correlation statistic. This is a statistic that's very similar to what is done in LIGO, actually. To basically to figure out what the SNR is in the statistic to see how likely it is that we'll make a detection. And this optimal cross-correlation actually accounts for the shape of the gravitational wave spectrum, as well as potential intrinsic red and white noises that might be underlying in our data. This is a very strict test. It doesn't rely. So it doesn't rely only on the self-noise of the terms that are sitting in the likelihood. And let me explain that for a second. So remember the pulsar has an Earth term. The gravitational wave is an Earth term and a pulsar term, right? So the perturbation at the pulsar when the pulse was emitted, and what it is on Earth when the pulse is received. Now, if you have a stochastic background, that's the pulsar term is going to be some red noise process. A stochastic background is going to be some red noise process, which is going to be different from pulsar to pulsar. And so if you find but the Earth term is going to be correlated among all pulsars. But because you can't say that a red noise process of a pulsar is definitely a gravitational wave, we can only rely on the part of it that's cross-correlated. And that's what I mean by this perhaps mysteriously written statement. Okay, so there's actually a really good reason for doing this. Oh, I just said that, okay. We don't know the slope of the spectrum and the red noise in the autocorrelation matrices. It could arise from something called spin noise in pulsars. We see those in regular pulsars, not in millisecond pulsars, except for with one exception, which obviously a pulsar that we do not use to detect gravitational waves, or could also do from effects of propagation in the interstellar medium. So the only way to be certain that we have detected a stochastic background is to really ensure that the data are cross-correlated. So that statistic is constructed in exactly that way. It's actually not a really good, it's actually a terrible upper limit statistic. There are much better ways to do upper limits, but in terms of detection, to be absolutely sure, you want to look for the signal in the cross-correlations. And the way I look at this analysis that we did is really a proxy for what I want to do, what we are actually doing in practice, which is a full Bayesian study where you compare evidences of models with correlated and uncorrelated noises. I mean, this is what we do with a real data set. What we do to get analytic expressions to see how things will scale are a little bit different, but simpler, but equivalent. Okay, so what did we find? So what we found was that the scaling behavior of this power, the signal-to-noise power in the cross-correlation really depends on the timing residual power spectrum. And so here's a simplified picture where the power spectrum of the residuals just has some white noise piece. Delta t is just the sampling rate, or 1 over the cadence. Sigma is just this RMS. And then it has a gravitational wave in it as well. So half of it is correlated, the Earth term. The other half, the pulsar term, is uncorrelated. So this is some red noise process, which we can write like that. So B, some coefficient times up to the minus beta here. And there are 3 regimes. So here I've written the, I've put the white noise level here, sigma squared delta t. One possibility is that all the gravitational wave power spectrum is below the white noise. Another possibility is that some of it is sticking up at low frequencies, but is hiding at high frequencies. And the other possibility is that the gravitational wave power spectrum dominates at all frequencies. Those are the 3 simple possibilities that we can have. So what we found, this is a really easy calculation to do, is that the signal-to-noise ratio in the cross-correlation statistic, when you're in the weak signal limit, just scales exactly like I said before. It's some strong power law. This is the t to the beta, right? Beta for supermassive black holes is like 13/3. All right, so you just wait. This is you just have to wait. Scaling law. And then in the intermediate regime, we found this completely different change in the way things scale. So now you go from scaling like a large power of time to only scaling like the square root of time. So you can't just wait anymore, okay? And then this quantity here, c times the amplitude of the background squared divided by sigma squared, that's actually the frequency. This thing has dimensions of frequency, and it's the frequency at which the white noise and the red and the gravitational waves are equal. The 2 power spectra are equal. That's what this is. And the scaling with a number of pulsars stays exactly the same. And But now you have a very weak dependence both on the time and on the cadence, and also on the RMS of the pulsar. So if you spend more telescope time trying to beat down on that white noise, it just doesn't buy you as much anymore as it does when you're sitting down here. And that was really a surprise, and it took a while to convince people that this was right. The last one, the top one, is irrelevant. I figured I should just mention it for completeness. Okay, so when are we in this intermediate regime? It turns out that it's sooner than you think. So you basically ask the question of when the lowest frequency bin is greater than the white noise, and you can solve for the white noise RMS that would the condition on the white noise RMS. And so if you have a 5-year-long data span with this 10 to the minus 15 typical stochastic background amplitude, this RMS is 304 nanoseconds. In our latest data release, 6 of the 17 pulsars had a better RMS than this. So it is possible that we're already in this regime, and we're not, we can't just wait. And actually, the best thing to do in that case is actually to add more pulsars to the array. That turns out to be the single best thing that you can do. And I wanted to point out that just because the lowest frequencies of the background are starting to creep up over the white noise of the pulsar does not mean that all of a sudden you see a lot of red noise in the pulsar. If you compute the RMS, and I don't have that table here, but if you compute the RMS of the actual red noise RMS, the induced RMS from the red noise process itself, it's something like 1/20th of this, something like 10 nanoseconds or 15 nanoseconds or something like that. So much, much smaller. It wouldn't be something that's sort of obvious in the data, just by looking at it. So here's a time domain. This is a full time domain simulation, and I include a timing model for this sort of canonical or theorist pulsar timing array. 20 pulsars, a cadence of 20 points per year, 100 nanoseconds, and here is this nasty surprise happening at late times that we saw. We saw this nasty behavior in the more complicated simulation that we ran first with a full thing, and then we went back and said, oh, wait a minute, we need to make things a little more simple so we can understand it. So we started simulating these theorist arrays. And I actually, the integral that you have to do to get this is it's actually a little bit tricky. It's sum of hypergeometric functions, and I don't have that here, but I can actually sort of approximate them and sort of get a good fit starting up here as well. So it's not just this sort of scaling, but you can actually, anyway, it was quite fun to do that. So that's what one pulsar timing array looks like. And this sort of then begs the question, well, what should one do? Suppose you have 20 pulsars that you time with a cadence of 20 points per year. M times C is your total time, right? So that's basically how many pointings you do per year, right? Or you can do 80 pulsars with a quarter of the cadence, right? So that's the first two, the black and the gray. So this is more pulsars timed with less cadence, but they're both the same. And then you look, and then this is what happens basically. Early on, there's not much of a difference between the two. In fact, the way I've written the expressions, they should actually be identical. They're not identical because those equations that I've shown you don't have the cross-correlation factors. But once you factor those in, you do a little bit better with 1 and 80. But anyway, they're basically very close. But as you wait longer, all of a sudden, the fact that you have better cadence doesn't help you anymore. Now, what helps you is that you have more pulsars. So if you had a choice, you start doing this. What should I do? Should I time 80 pulsars with a lower cadence or 20 pulsars with a higher cadence, given that they all have the same RMS? You want to do the top one. So okay, I think that's probably all I wanted to say about this plot. Anyway, so the full time domain simulations, including the timing model, gives us some conclusions. The first thing is that increasing the cadence and improving the white noise helps you when the gravitational wave signal is buried in the white noise. But as time goes on, that the gravitational waves start to creep out at the lowest frequencies, and that's not the right thing to do. So long term is not the thing to do. And the reason that that's happening is because the signal to noise ratio is dominated by what's going on in the lowest frequency bins. Now, at some point, these become gravitational wave dominated, and then the dominant contribution to the noise is not the white noise anymore. It's actually the uncorrelated pulsar term red noise. That's what's actually contributing most of the noise at those frequencies, clearly. And the most effective way to beat down this uncorrelated part of the gravitational wave signal is to add more pulsars to the pulsar timing array. And then this is true for stochastic backgrounds. It doesn't mean that we shouldn't work hard to improve our RMSs. I want to say that it's really good to improve our sensitivity because these are actually critical to other types of sources. This is just for stochastic backgrounds. If you're thinking of continuous waves, for example, and individual sources, working on your RMS and your cadence is actually it really is the best thing to do. Okay, so I have 2 more minutes, and I think I can get this done in 2 more minutes. Okay, so testing gravity. Why do this? I think we don't need to go through this right here. We want to understand if we can unify gravity and quantum mechanics, and we want to understand the pi of the universe, the dark energy, and potentially the dark matter as well. Okay, so what happens in alternative theories of gravity? There's two potential differences. One of them is that the gravitational wave polarization states increase or can increase. In general relativity, as I mentioned at the beginning of the talk, we only have 2 polarization states. And this is easy to explain. The metric perturbation has 10 independent components because it's a 4x4 symmetric tensor. We can do 1 coordinate transformation. We always have that freedom. That removes 4 components. And then in GR, it turns out we can also work in the Lorentz gauge, and that also removes another 4 additional components, leaving 2. But in general, we cannot impose a Lorentz gauge. But we're still always left with this. We should always be able to do our general coordinate transformation. So these 10 independent components minus these 4 coordinate transformations that we should always be allowed to do leaves 6 degrees of freedom, and that's why there are 6 modes. The second difference is that gravitational waves may propagate with speeds that are smaller than light. For example, in massive gravity, where gravitons have a dispersion relation. So I don't have a cool animation for this, unfortunately. But this is the plus mode that I showed you before. This is the cross mode that I alluded to. It's rotated by 45 degrees. So these are so-called tensor modes. Then there's 2 scalar modes. A breathing mode, which actually stretches and squeezes the string of particles, and a longitudinal mode, which acts along the direction of propagation of the gravitational wave. And there's an additional two vector modes as well that can arise. So that's what those modes will do to a ring of particles. This is what the antenna patterns look like. And what an antenna pattern is how sensitive you are to a gravitational wave, in this case, as you move the pulsar around. So I fix the gravitational wave direction. It's going up. And then I'm free to move my pulsar around. And the plus and cross polarizations look like this. The cross is just a version of this, but rotated by 45 degrees. So I'll just put 1. Here's what the vector modes look like. This is what the x look like. The y looks like the same thing, but rotated 90 degrees because it's a vector mode. And then you have the 2 scalar modes, which are rotationally invariant. And this is what the breathing mode looks like. This is what the response of the breathing mode looks like. And this is what the response of the longitudinal mode looks like. And actually, this kind of diverges as you bring the pulsar, as you make the direction of the pulsar and the direction of the gravitational wave anti-parallel. So what is the effect of these extra modes? Well, the effect is to change this. One effect is to change the expected cross correlation. So I showed you before. I said, when you cross-correlate 2 pulsar timing residual data streams, that the correlation in those data sets is a function of the angular separation here on the x-axis. And I showed you this curve. It used to be red. Now it's blue. So that's for the plus and the cross modes. But the breathing mode, for example, has a different one. So the effect of one effect on the stochastic backgrounds is actually to change the expected shape of the Hellings and Downs curve that we will measure in our data set. I'm going to skip this stuff because there's no time. I also mentioned the speed of gravitational waves. So I just talked about the polarizations. I also mentioned the speed of gravitational waves. This is really probably more of a LIGO thing than a pulsar timing thing, but I thought I'd mention it anyway since I was talking about tests of gravity. There are a couple of papers that I've seen with EM signatures. I think David Kaplan and Richard O'Shaughnessy and possibly other people have written papers on this, but there's not enough for me to say for sure that this will work. With LIGO, it certainly will. So as I mentioned, we could have different differences in the propagation velocities, and of course, if we can have coordinated electromagnetic and gravitational wave observations, we can place stringent constraints on the speed of propagation. And the reason for that is that even if the speed of gravitational waves and the speed of gravity is different to 1 part in 10 to the 15, because these sources are, hundreds of megaparsecs away, the time of arrival really builds up over those huge distances, and you can actually, constrain that very well. Modulo, of course, we understand the emission mechanism well enough. So this is some kind of acute thing that happens if you have a massive graviton. You're going to have dispersion as it travels, and so lower frequency waves will arrive later, and you effectively get a squeezing of the gravitational wave, which is kind of cool. So that's one effect. Another is a whole set of biometric theories that are used to explain galaxy rotation curves. Personally, I don't really like modifying gravity. I hope I'm not upsetting anybody here. I don't really like modifying gravity to explain dark matter, but just because it seems so hard to try to do that and the acceleration. But anyway, some people do this, and in order to make these work, you actually end up with huge time lags, like more than a day, sometimes a month or something. So basically, we'd never see an EM counterpart, because we'd never think to look, a month later or whatever. But my expectation is that these theories will actually be that we will see a GRB, within a coincident time, which is much less than a day, and rule out all of these theories. Okay, so my conclusions are still correct, even though I skipped about a third of my talk. So I hope I've convinced you that pulsar timing experiments can be used to observe the low-frequency gravitational wave universe. That a detection and inaugurating that era of looking at the universe with low-frequency gravitational waves could begin within the decade. And then at the end, I also discussed how these gravitational wave observations can also be used to test gravity. Thank you.
So say you make an observation of stochastic gravitational wave back home. What type of inferences about the universe will you then be able to draw? Can you say something about cosmic strings, about supermassive black hole mergers? What type of things will you be able to say?
That's a great question. So right away, the detection threshold that we use, that I like to use, and I guess maybe this is still up for discussion with the rest of them. So I'm using 3 sigma. As my detection threshold for stochastic background. And the reason I do that is because we only have one realization. So there's no trials factor. We have one realization. We have one data set. The signal is all sitting at low frequencies. And so we just, now, so if you buy that, you may or may not like that. But if you buy that, right away, of course, with 3 sigma, we won't be able to say very much. So, one thing you could do is try to measure the shape of that spectrum. Now, how can we determine what are the error bars or the amplitude and the slope? That's what's going to tell us whether things are cosmic strings or supermassive black holes. Or there's also a whole set of issues involved with what the solution is to a last parsec problem. If it's stars or gas and whatever, that actually changes the shape of the spectrum as well. So with a signal-to-noise ratio of 3, right, when we detect something, we can't actually measure those things. Those things have very big error bars. But in anticipation of this question, which pops up every once in a while, we did run some simulations. And to try and figure out at what point, at what signal-to-noise ratio we can actually measure say the spectral index, with what kind of an error bar or the amplitude. It turns out that that SNR is just twice that. It's just 6. Now that seems like a long way. We are an SNR of 3. How are you going to get to an SNR of 6? So these simulations, we also showed that because we're adding many pulsars to the array every year, something on the order of 4, the second pulsars every year, we actually gain, currently we would gain about 1 unit of SNR every year. So if we make a detection tomorrow with an SNR of 3 in 2017, I can tell you whether it's supermassive black holes or cosmic strings or perhaps something about the solution to the last parsec problem.
You've got an average of 40 here?
Yeah, actually, yeah. Even lately, it's even been a little bit more, but that's a little. It turns out when we put in the new instrumentation that has much more bandwidth, people started looking at old pulsars that had been thrown out because in that particular band that we had access to, they just weren't that bright, so they were thrown out. But now, we go from 64 to 800 megahertz. Suddenly, these pulsars that were kind of nice MSPs, but not. Now we have much more band, and it turns out that they are sufficiently bright to be active. We've had kind of like a bump recently, but on average it's been four per year from pulsar surveys. So these are all sky surveys that we run ourselves, all sky surveys that that are run out of other telescopes, and also lately the Fermi sources. Those have contributed quite a lot as well. So these.
Fraction of pulsars in the galaxy have you seen?
Let's see if I can remember the numbers.
What's the furthest one?
I think there are 200,000. I think that's the estimate. And we see now 2,000.
Plus you got plenty of room.
Yeah, well, right, but then those other ones are really far away, right? So it's things like with the SKA, for example. That now, having said this, I don't have a plot of this with me, but we have plots of the brightness of pulsars that we discover as a function of time, and it seems pretty flat. So we're still running, surveys. We're still finding bright things. That seems to be still working. And given this sort of 5-year or 10-year timeline, I'm not too worried that we're going to run out of pulsars just yet. In the future, of course, we'll have the SKA and other telescopes. Those are the ones that are going to find the 20,000 or 100,000. I can't remember. Basically, all of them.
I was wondering what kind of noise you get from the ISM, because you have to imagine that as the galaxy rotation happens, you change the dispersion measure by some small amount for each pulsar, and it could be in a correlated way in a given direction. It's not something I normally worry about, but when you're looking at these tiny values.
Yeah, no, we worry about that a lot. I mean, I think it definitely keeps some people up at night. So like as I mentioned, we measure we do measurements at 2 different frequencies that are offset, but that are far away in frequency. So say 800 megahertz and 1.4 gigahertz. And then you basically try to measure what the dispersion is doing at that particular time and how that's changing in time. And we keep track of that very accurately as we can, with as much signal to noise as we can, because we're going to subtract that out of the data. Of course, the degree to which we can subtract it out depends on the signal to noise that we have to measure the effect. And there's going to be some residual effect left in there. There's no question about it. And the question is, so I think what you're asking is, what is that? And so far, no. So right now, from what so we just had a meeting, and I actually asked this question to the people that work on this. And I think they said something less than 10 nanoseconds of this process. The other thing you might worry about, so you mentioned also modulations depending on where the Earth is and what the ISM is doing, and we see those too. I mean, there's yearly periodicities in the dispersion measure corrections that we apply to the pulsars. Sometimes we see unexplained spikes. We sort of measure these things, but the idea is that we're measuring it with sufficient precision that we subtract it out. Now, whatever remains, it depends on the suppose the interstellar medium effects are also a red noise process, which if there's turbulence in the interstellar medium, that's what you would expect. Then the question is.
Expected to average out of the line of sight, right, for turbulent processes.
So okay, I don't know why that's not right, but I think that's not. So over the course of time, this thing builds up. So you basically have a red noise process which kind of can compete with a stochastic background. So the question then is, what's the slope of that sort of turbulence-driven effect? And if it's steeper than the stochastic background, then we're SOL. It turns out it's not, fortunately. So it's something like a slope of -2, and what we're looking for is a slope of -4 or something. But yeah, that could certainly come in. That could certainly hurt us.
How is the final parsec problem just isn't the problem and supermassive black holes don't merge? Like, how long would it take you to decide that?
So I'm not an expert on this, but from what I hear, nobody cares about the final parsec problem. I mean, I'm sorry. Let me backtrack a second. People think that the last parsec problem is somehow solved. Like people don't really think that there is no solution to it. In fact, my worry is actually the opposite, that it's solved too efficiently by things that are not gravitational waves. So if we have a lot of stars and a lot of gas, you're going to have black holes getting closer to each other, not like in my cartoon because they're emitting gravitational waves, but because there's a lot of stars and gas around, bringing them together, gravitational wave emission is then reduced, and then we might not be able to detect it. I think that's. There's actually people in the audience that know way more about this
That's
than me.
probably more important for the lower mass black hole, like in the 60s, not the 80s and 90s. You can work out and then the period is in the range of a year or a few years what the merging time is, right? And in practice, the time scale for the gas to do dramatic things in the galaxies when they're merging is the order of, I guess, 10 to 30 million years. If the merging time is much less than that, then potentially, gas might have helped get the black holes that close, but by that point, gravity waves are taking over. That's just a rough number. But
And you
Cool.
said that the big holes, so
Yeah,
you
yeah,
don't have to worry about it.
right. So 10 to the 9. So solar mass black holes are the typical.
All right, well, let's have you one more back to the folks.